As an example of a concave mirror situation, we've got here an object which is sending light rays into the mirror, and the mirror is reflecting the light rays, producing an image as seen there. So we've got the object where the distance of the object from there is 12 centimeters, as we've seen down here. Distance of the image, di, that is 4 centimeters, and we're told the height of the object and the height of the image. First part we have to ask, we have to answer, I guess, is the magnification. What is the magnification? There's two ways we could do that given the information we have. It's either the height of the image over the height of the object, or it could be the distance of the image over the distance of the object. Excuse me, so let's just stick with our height for now. So we've got 2 centimeters over 6 centimeters, meaning our magnification is 1/3. That means it's 1/3 of the original height, or if we're writing that as decimal, 0.333 recurring. So let's just write it like that. No units for magnification because you're dividing a distance measurement by another distance measurement, and the two distances in centimeters cancel out to produce no units. So there's no unit for magnification. Very important. Next part, B, would describe the nature of the image. Well, we've already seen from the magnification that it is diminished. That is, it's smaller than it was as an object. It is a real image because it's on the same side of the mirror as the object, and you could project this one on a screen if you put a screen in position where the image is. So that's real. And the other thing is it's inverted because it's upside down. Inverted upside down. Okay. C. To answer C, we're asked, what is the focal point? Okay, now there's a couple of ways we could approach this. We could draw a scale diagram and work that through, or we can use Descartes' formula, plus 1 over dO. Okay, I favour Descartes' formula, so we will do that. So bring this, everything's positive in this, which is nice. All the values, dO is positive, di is positive, and we know that there'll be a focal length will be positive as well, because it'll be on the positive side of the mirror over on this side and not this side. So let's just come across a little bit to do the calculations. Coming up the top here, we've got 1 over f, which we're trying to find out, equals 1 over di, which is 1 over 4, plus 1 over dO, which is 1 over 12. Interestingly, you have to be very careful with your units, because if you change between meters and centimeters, you can end up with some very funny things going on, and often you're given results like you might give in this dO as 0.12 meters, and you shouldn't put that into these. You shouldn't put it in meters, because fractions you can't deal with decimals properly, especially if one of them will be a decimal fraction and one of them won't be. Then you're going to have all sorts of problems, trust me. So we're sticking with the centimeter units. It means our focal length will be in centimeters as well. So we need to find a common denominator. 4 times 3 gives us 12, so we can multiply this term by 3 over 3, which will give us 3 over 12 plus 1 over 12. So that gives us a nice common denominator, and we can add them up to get 4 over 12. And that means our focal length, because this is 1 over the focal length, our focal length will be 12 over 4. We've inversed both sides. 1 over f equals 4 over 12, so f over 1, which is just f, equals 12 over 4, which is 3 centimeters. So that's our focal length. Okay, nice. Coming across, we are asked what will happen if dO, that is, well, where's my colour? Change my colour. If dO here is moved closer by 1 centimetre. So now we've got the object. Well, the object has moved closer, decreasing dO by 1 centimetre. What's going to happen to the image? Okay, now we know that parallel light rays will go to the focal point. What do we, DO was 4 centimeters. This is 3 centimeters for F, as we calculated in the previous one. So we know that the further away that the object gets, the closer the image will get to the focal point, because parallel light rays, which are far away light rays, will focus at the focal point. So in this case we're moving the opposite direction, so we're moving the object closer to the mirror, so it stands to reason that we will find that the image will move further away. Excuse me. We could also perform some calculations to see what will happen to the height, to DI, to the distance image, if we were to plug it into Descartes' formula with our focal length 9. 1 over 11 is now our DO, plus 1 over DI. We don't know what DI is, but remember F we calculated was 3 centimeters. So that's a bit of a tricky calculation, so I'm not going to do it, but we should know that as the image moves further away from the mirror, it should get larger. And as the position of the object gets closer and closer to the focal point, that image will get progressively larger and further away. As soon as the object's at the focal point, you won't get an image because the light rays never meet. But yeah. Okay, so that's it.